As a back-end engineer, you're pretty used to writing, deterministic code.
Right. Totally predictable.
Exactly. Like input A always yields output B. You route a request through an API gateway. It queries a specific index in Postgres, and it returns a highly predictable JSON payload.
And if it fails predictably.
Yeah, exactly. You get a defined error code, a 200 OK or, a 500 internal server error.
Yeah.
It is a world of absolute binary control.
Which is very comforting.
It is. But what happens to your entire software architecture when your core processing engine starts, when it starts hallucinating?
That's the terrifying part.
Right. What happens when you replace that predictable database query with a call to a system that is inherently wild and, probabilistic?
I mean, your traditional error handling paradigms just completely disintegrate at that point.
They really do.
You can't just wrap a standard try-catch block around a system that confidently returns a beautifully formatted, syntactically perfect, but factually entirely fabricated response.
Yeah, the compiler doesn't care if it's a lie.
Exactly. You are no longer managing discrete state changes. You're managing statistical probabilities.
And this is the brutal reality of the shift we're in right now. You, the listener, have spent years mastering microservices, load balancing, distributed systems.
New shard stuff.
Yeah, you understand the back-end stack intimately, but now the industry is throwing this massive curveball at you called AI engineering.
And the hype is just deafening.
Oh, it's everywhere.
Yeah.
The tools seem to change every 48 hours. And you're trying to figure out how to actually architect and build robust products with this technology without building a system that collapses the moment a user inputs, like an edge case prompt.
The fatigue is so real, especially for seasoned engineers who have seen hype cycles come and go.
Web3, anyone.
Right, exactly. So it's crucial to separate the fundamental, lasting architectural shifts from the flashy wrappers that are just going to be obsolete by next quarter.
So today's deep dive is designed to cut right through that noise. We're taking a purely engineering-focused look at this transition.
No fluff.
No fluff. We're anchoring our discussion in the foundational framework laid out in Chapter 1 of the book AI Engineering by Huyen.
Such a book.
It really is. It's this rigorous analysis of the leap from traditional bespoke machine learning to this brand new discipline of building applications on top of foundation models.
And Huyen's work here is essential because she doesn't just, list out the new tools. She deconstructs the underlying mechanics.
She gives you the blueprint.
Yeah, a structural blueprint for how these models actually function, why the engineering stack has fractured into 3 distinct layers, and most importantly, where a traditional software engineer fits into this new hierarchy.
So we are going to unpack the actual math and logic behind how large language models learn. We'll dive into the mechanics of self-supervision and quantization.
Which sounds intimidating, but it's really not.
It's just math. We'll map out those 3 layers of the modern AI stack: infrastructure, model development, and application development, and translate them into back-end concepts you already know.
Bridging that gap.
Exactly. We will dissect why the traditional engineering workflow has been violently flipped on its head.
That's a huge one. Moving from a data model product pipeline to a product data model reality.
And we'll examine the hard empirical data on where these systems are actually generating enterprise value right now, from workflow automation to ARGE architectures.
Real-world use cases.
Yeah, so by the end, you will have the mental models required to map your existing back-end expertise directly onto the AI engineering stack.
But to build on top of these systems, we have to start by reverse engineering the paradigm shift that made them possible in the first place.
We have to know how the engine works.
Right, because for a decade, AI was largely restricted to classification tasks.
Like recommending a movie.
Yeah, or flagging a fraudulent transaction, or classifying an image as a hot dog or not a hot dog.
The classic Silicon Valley example.
Always. But suddenly, it transitioned to generation and reasoning. And the catalyst for that transition boils down to one primary factor.
Scale. Unprecedented, almost incomprehensible scale. Let's quantify that scale, because in traditional back-end terms, scaling usually means spinning up a few more Kubernetes pods to handle a traffic spike.
Or sharding a database.
Right. But we aren't talking about horizontal scaling of web servers here.
Not at all. We are talking about scaling the neural network parameters and the training compute to a degree that actually alters global supply chains.
It's wild to think about.
It is. The models powering tools like ChatGPT or Google's Gemini or Anthropic's Claude Agiri, they're so massive that training a single frontier model requires tens of thousands of specialized GPUs running continuously for months.
And the power requirements.
Oh, the energy draw is so severe that tech companies are actively negotiating with nuclear power plants.
Wait, literally nuclear power plants?
Literally, they are trying to secure dedicated gigawatt-level energy pipelines just for these data centers.
And the data constraints are just as severe. I mean, we aren't just parsing a few terabytes of application logs here.
No, we are scraping the absolute limits of human-generated information. These models have ingested a significant percentage of the publicly available, high-quality text on the entire internet.
That's hard to even wrap your head around.
It is. Researchers are genuinely modeling the date, and it's sometime in the very near future when we simply run out of fresh human text to train the next generation of models.
We just run out of internet. This creates a really fascinating bottleneck. Because in traditional software, if I want to build a competing search engine, it's hard, but I could theoretically rent enough AWS instances to crawl the web.
It's a capital problem, but it's doable.
Right, but if I want to build a frontier AI model from scratch today, I literally cannot buy the GPUs. The waitlist is years long.
And even if you could get them, you probably can't afford the hundreds of millions of dollars in raw compute costs.
Which forces a massive architectural shift for the rest of the industry, because training these foundational models is now restricted to this tiny oligopoly of megacorporations with the capital to build these hyperscale server farms.
And the resulting artifacts, these massive models, are then made available to developers as model as a service.
So as a back-end developer, my capital expenditure for AI infrastructure is basically zero. I don't buy GPUs.
You buy API credits.
Exactly. My infrastructure shifts from managing metal to managing network latency, API rate limits, and token economics.
That is the crucial pivot. You are outsourcing the most computationally expensive process in human history to an API endpoint.
Which is incredibly convenient.
It is. But to effectively utilize that endpoint, you really have to understand what happened during that massive training run. Because just throwing more computers at the old machine learning algorithms wouldn't have produced these results.
So what was the actual breakthrough?
The breakthrough was a fundamental shift in the training mechanism itself. We moved from supervised learning to self-supervision.
Let's translate this for the audience. Supervised learning, the old way, is essentially manual data entry, right?
Yeah, pretty much.
Like, if I wanted a system to recognize fraudulent network traffic, I had to hire analysts to manually review thousands of packet logs, explicitly tag the malicious ones with a Boolean true, and feed that structured, labeled data set to the model.
And that approach was entirely bottlenecked by human annotation.
It's just too slow.
It's expensive, it's slow, and honestly, it's mathematically fragile.
Why fragile?
Because it only teaches the model to recognize the specific patterns the human labelers were looking for. It doesn't generalize well.
Ah, I see. So self-supervision eliminates the manual data entry entirely. It's more akin to, like, taking a system and dropping it into an ocean of raw, unstructured server logs and telling it to simply figure out the underlying network protocols on its own.
Just by finding the statistical relationships between the bytes.
Exactly.
With language models, that statistical game is predicting the next token.
The famous autocomplete.
Right. You feed the model a sequence of text scraped from the internet, say, the quick brown fox jumps over the lazy,
Yeah.
and you hide the final word. The model calculates a probability distribution across its entire vocabulary and guesses the next token. If it guesses car, it calculates the error, the cross-entropy loss between its guess and the actual word dog, which was already there in the raw data.
And then it adjusts itself.
Yes, it propagates that error backward through its billions of parameters, slightly adjusting the weights to make dog more likely the next time it sees that specific context.
So because the data already contains the answer, the next word, it labels itself.
Exactly.
Like that's the self-supervision. That means I don't need human labelers at all. I just need a giant web scraper and massive storage.
That's the beauty of it. You can run this prediction loop trillions of times across Wikipedia, GitHub repositories, Reddit threads, scientific papers. It just learns from everything.
Okay, I have to push back here because this is the exact point where skeptics, especially senior engineers, roll their eyes.
I hear it all the time.
They look at this mechanism and say, so it's literally just autocomplete. It's a stochastic parrot calculating statistical frequency.
The stochastic parrot argument, yeah.
If the foundational loss function is solely optimizing for the prediction of the next token in a sequence, how does that mathematically result in a system that can, like, debug a complex Python script or synthesize a summary of a 50-page legal contract? You can't achieve complex reasoning just by memorizing word frequencies.
That intuition is so common, but it severely underestimates the demands of the loss function at scale.
Okay, unpack that for me.
If the model was only trained on a few megabytes of text, it would just memorize phrases.
Sure.
But when you force a neural network to minimize prediction error across terabytes of highly complex, diverse data, simple statistical memorization becomes mathematically inefficient.
It just runs out of space.
Exactly. The network runs out of capacity to just memorize everything.
Right.
It has to find a compression algorithm.
Oh, that makes sense. A compression algorithm.
Precisely. The most efficient way for a neural network to compress the data of the internet and consistently predict the next word in a physics textbook is not to memorize the textbook.
It's to learn the physics.
Yes. It implicitly learns the underlying laws of physics that govern the text. If the prompt is a half-written Python function, the most mathematically efficient way to predict the next lines of code is to develop internal representations of Python syntax, variable scoping, and logical loops.
So the next token prediction is just the forcing function. The actual byproduct of that massive optimization process is a highly compressed internal model of the world's logic.
Exactly. The model doesn't know it is learning logic. It is just ruthlessly minimizing cross-entropy loss. But the structure of the data it is training on human language is fundamentally governed by logic, causality, and facts.
So by modeling the language perfectly, it ends up modeling the logic embedded within it.
That's the secret sauce of scale.
Okay, this makes perfect sense for text. Text is sequential, but we are rapidly moving beyond text. We're dealing with large multimodal models now, LMMs.
Oh, yeah, the game has changed again.
I can pass an image of a handwritten database schema to an API, and it will generate the SQL to create those tables. How does a system trained on sequential text prediction suddenly understand two-dimensional pixel arrays?
This was the next major unlock, and it was driven by a technique called natural language supervision. It was pioneered by models like OpenAI's CLIP back in 2021.
What did they do differently?
Well, they didn't go back to the old way of having humans draw bounding boxes around cats in images.
That would take forever.
Right. Instead, they scraped the internet for image-text pairs that co-occurred naturally.
Like an HTML image tag where the alt text describes the image?
Yes, exactly that.
Yeah.
They amassed 400 million of these pairs. Then they trained two separate encoders, one that converts the text into a mathematical vector, an embedding, and another that converts the image into a vector.
Okay, two vectors. Then what?
The training objective was simple. Adjust the weights of both encoders so that the vector for an image and the vector for its corresponding alt text are pushed closer together in a shared mathematical space.
While pushing unrelated ones apart.
Precisely. Pushing the vectors of unrelated images and text further apart.
So they are using cosine similarity. They're mapping pixels and text into the exact same high-dimensional coordinate system.
Exactly.
So the word database and an image of a database schema end up occupying the same neighborhood in this latent space.
This bridges the gap completely. The visual concepts become inextricably linked to the semantic concepts learned during the text training.
And this amalgamation of text, code, and image understanding leads us to the current paradigm, right? The foundation model.
Yes, the foundation model.
And a foundation model is fundamentally different from a traditional microservice architecture. I mean, in traditional ML, if I was building an e-commerce platform, I would build one bespoke model to power the product recommendation engine.
Right, a highly specialized model.
And then I'd build a completely separate sentiment analysis model to flag angry customer reviews. And a third model to translate the UI into Spanish.
It was a highly fragmented, highly specialized ecosystem. You had a different model for every single feature.
But foundation models consolidate all of that.
Completely. Because of their scale and the generalized nature of their world model, a single foundation model can perform all three of those tasks. Recommendations, sentiment analysis, translation right out of the box, with zero task-specific retraining.
It's the ultimate monolith. It's a general-purpose engine. So knowing that we have access to these massive, generalized, multimodal engines via API, how do we actually structure our engineering teams around them? Where does a back-end engineer fit into this ecosystem?
That is the million-dollar question.
Chip Huyen breaks this down into a three-layer stack. Let's dissect layer one first. Infrastructure.
Okay, at the absolute bottom of the stack, you have infrastructure. This is the hardware layer and the orchestration layer required to train and serve these models.
We're talking about compute management, massive distributed file systems, network interconnects, production monitoring.
Everything needed to keep the metal running.
On the surface, this sounds exactly like a DevOps or site reliability engineering role. But the underlying hardware constraints are completely foreign to a standard backend environment, aren't they?
They are drastically different. A traditional back-end infrastructure is heavily CPU-centric and highly transactional. You're optimizing for concurrent connections, rapid database reads, low-latency stateless HTTP requests.
Right, I'm watching my CPU utilization graphs.
But the AI infrastructure layer is entirely GPU-centric. The bottlenecks shift dramatically. You are no longer primarily bound by network I/O.
What are you bound by?
You're bound by memory bandwidth on the GPU itself.
Right.
The physical speed at which you can move massive matrices of weights from the GPU's VRAM into its compute cores.
And I imagine the orchestration is different too. Like if a single web server goes down in a traditional cluster, the load balancer just routes traffic to the others. No big deal.
Exactly. Stateless is easy. But if a single GPU fails during a synchronized training run across 10,000 GPUs,
Let me guess, the whole thing crashes.
the entire distributed state can crash. It requires incredibly complex checkpointing and recovery protocols just to keep the training run alive for months at a time.
That sounds like a phenomenal engineering challenge.
It is. But here is a really interesting data point from Huyen's analysis. If you look at the growth of open source projects on GitHub, the infrastructure layer is not where the explosive growth is happening.
Really? Why is that? With all these new GPU clusters being built, you'd think DevOps would be reinventing everything.
Because the core infrastructural paradigms, orchestrating containers, monitoring resource utilization, managing data pipelines, they are largely mature.
Oh, I see.
The existing tools like Kubernetes or Prometheus, they are simply adapting to support GPUs. The foundational principles of infrastructure haven't required a total rewrite, just an expansion of capability.
Which brings us to layer 2, model development. If layer 1 is the metal, layer 2 is the factory where the models are actually designed, trained, and optimized.
This is the traditional domain of the machine learning engineer or the AI researcher.
And this involves defining the neural network architectures, like the transformer, and dealing with the massive data engineering required before training. A huge part of this is dataset deduplication, right?
Yes, deduplication is massive.
Let's pause on deduplication for a second. In a standard Postgres database, a duplicate row is just, a minor waste of storage. Why is it a critical failure in model development?
Because if a foundation model encounters the exact same sequence of text hundreds of times in its training data, it fundamentally alters the loss function we discussed earlier.
How so?
The model stops trying to learn the generalized logic behind the text, and it simply memorizes that specific sequence to lower its error rate quickly.
Ah, taking the easy way out.
Exactly. This leads to overfitting. When a user prompts the model later, it will regurgitate that memorized text verbatim.
Which causes severe issues with copyright infringement.
Copyright infringement, data privacy leaks, and just a general lack of creative generation.
Right.
It becomes a parrot.
So how do they fix it?
They use probabilistic data structures, things like min-hash, to identify and strip out roughly similar documents across terabytes of text before the training even begins.
And then they have to tokenize that data.
Right, tokenization.
Tokenization is a concept every backend engineer working with AI needs to understand immediately because it directly impacts your latency and your cloud bill. A token is not just a word, right?
No, not at all. Models don't read words, they process numbers. Tokenization is the algorithmic process of breaking raw text into subword chunks and assigning each chunk a unique integer ID.
So how does it decide where to cut the word?
Most modern models use byte pair encoding, or BPE. It analyzes the frequency of character sequences. Common words like the might be a single token, but a complex word like unbelievable might be split into unbelieve and able, 3 separate tokens.
And this matters because APIs charge you by the token, not by the byte. And models have strict context windows, the maximum amount of tokens they can hold in memory at once. If you're blindly passing massive JSON payloads into an API prompt without understanding how it tokenizes the brackets, the white space, the keys,
You are burning money and truncating your data. Every extra space character might be a token you are paying for.
that's a great tip for developers optimizing their API calls. So beyond data prep, layer 2 is also deeply concerned with inference optimization, right?
Yes, inference is hugely important.
Because once a model is trained, it is incredibly heavy. A 70 billion parameter model is essentially 70 billion floating point numbers.
That's a lot of math.
If each number is a 32-bit float, That model requires 280 gigabytes of VRAM just to load into memory, let alone process a request.
You can't just casually spin that up on a standard cloud instance. It requires multiple high-end GPUs just for inference.
So model developers use techniques like quantization.
Right. Quantization is basically mathematical compression.
They mathematically compress the model. They take those high-precision 32-bit floating point numbers and cast them down to 8-bit or even 4-bit integers.
Wait, if you chop off that much precision from the weights, doesn't the model instantly become stupid? You are throwing away so much data.
You would think so, right? But neural networks are surprisingly resilient to noise.
Really?
Yeah. By using clever calibration datasets during the quantization process, they find that you can compress the model by 70% while only losing a tiny fraction of its accuracy.
That's incredible.
It drops the memory requirement drastically, allowing the model to fit on a single GPU, which radically reduces the latency and the cost per API call.
This is fascinating back-end optimization. But let me ask the critical question. If I am a senior back-end engineer listening to this, do I need to be in layer 2?
That's what everyone asks.
Do I need to learn the underlying linear algebra of a transformer block? Or how to implement a custom quantization algorithm in C/A?
Absolutely not. And this is the biggest misconception keeping traditional developers out of AI. For the vast majority of software engineers, deep machine learning knowledge is not a prerequisite anymore.
It's just abstracted away.
Exactly. Because of the model as a service layer, the incredibly complex math of layer 2 is hidden behind an API gateway. You don't need to forge the Azure block. You just need to know how to build the car around it.
Which perfectly sets up the top layer, layer 3, application development.
This is the Wild West.
It really is. This is where the explosion of tools like LangChain, Llama Index, and AutoGPT is happening.
And according to the data, the growth rate of this layer completely dwarfs the adoption curves we saw for monumental web frameworks like React or Node.js.
But this is where the actual business value is generated. Application development in the AI era involves entirely new engineering primitives. And the first one is prompt engineering.
Prompt engineering gets a bad rap. It sounds like, typing polite requests to a chatbot.
Right. It sounds like a parlor trick.
But programmatically, it's about controlling state and steering probabilistic outputs.
Exactly. You are adapting the model's behavior at runtime without altering its underlying weights. You are defining system instructions, establishing few-shot examples.
Few-shot examples being where you provide the model with a few input-output pairs in the prompt itself to demonstrate the required format.
Right, and you're setting output constraints like demanding a strict JSON schema. It's not just talking to a bot, it's formatting a programmatic request.
It's essentially dynamic context injection. But the most important architectural pattern in this layer, the one that every single backend engineer needs to master today, is context construction, specifically AGE.
Retrieval Augmented Generation.
Yes, RAG. RAG is the architecture that bridges the gap between the frozen, generalized knowledge of a foundation model and the dynamic, proprietary data of your specific business.
Let's really break down the mechanics of RAG because it heavily utilizes concepts backend developers already know, just applied differently.
The problem our RAG solves is hallucination, right?
Fundamentally, yes. If I ask a foundation model, what is our company's refund policy? It will hallucinate an answer because it doesn't have access to my internal Confluence pages.
It's guessing based on the average refund policy of the internet?
Exactly. I need to inject my specific policy into its context window, but I can't inject all 10,000 pages of my company's documentation into every single API call.
That would cost thousands of dollars per request and immediately exceed the token limit.
So you need a retrieval system. The pipeline works like this. First, you have the data ingestion phase. You take all your internal documents and you chunk them into smaller, semantically meaningful segments.
Say a paragraph at a time.
Right, just standard text processing.
Then you pass each chunk through an embedding model. This is a specialized, smaller ML model that converts that text chunk into a high-dimensional vector representation.
Which is just a massive array of floating point numbers that captures the semantic meaning of that paragraph.
You are converting human language into a mathematical coordinate.
And then you store all of those vectors in a specialized infrastructure component called a vector database.
How does that differ from a normal database?
Traditional relational databases use B-trees to index data for exact keyword matching. Vector databases use algorithms like HNSW hierarchical navigable small world graphs.
That's a mouthful.
It is, but essentially, they index data based on proximity in that mathematical space.
So when the user types their query, what is the refund policy? What happens on the back end? Let's trace the request.
Your backend intercepts that text query. It sends the query to the same embedding model to convert the question itself into a vector.
Okay, now the question is a coordinate.
Then, you execute a similarity search against the vector database.
Yeah.
The database calculates the cosine similarity between the query vector and all the stored document vectors.
And it returns the closest ones.
It returns, say, the top 5 chunks of text that are semantically closest to the question.
So it finds the 5 specific paragraphs in our documentation that actually discuss refunds.
Finally, your backend takes those 5 paragraphs, concatenates them with the user's original question, wraps it all in a strict system prompt, something like answer the user's question using only the provided context, and sends that final payload to the foundation model API.
The LLM reads the context, synthesizes the answer, and returns it.
Boom. Done.
This is brilliant because it grounds the probabilistic model in deterministic data. You dramatically reduce hallucinations because the model isn't trying to remember facts. It is just executing reading comprehension on the text you provided.
Building robust RAG pipelines, handling the chunking strategies, tuning the retrieval algorithms, managing the vector database latency. That is one of those critical skills in Layer 3 application development right now.
But this layer also introduces massive new headaches, specifically around defensibility.
Oh, this is a huge topic.
If the core intelligence of your application is just an API call to a model built by OpenAI or Anthropic, what stops a competitor from building the exact same app over the weekend? The model itself is a commodity.
You're right, the moat is no longer the model. The competitive advantage is built entirely in how you engineer Layer 3.
It's the pipeline.
It's the sophistication of your RG pipeline. It's your proprietary data. It's how seamlessly you design the AI interface to fit into a specific user workflow.
So a generic chat UI is worthless.
If you build a generic chat interface wrapped around an API, you have zero defensibility. But if you build an agentic system that deeply integrates into a legacy enterprise database, orchestrates multi-step actions, and handles edge cases gracefully,
then you have an incredibly sticky product.
Exactly. This shift in where the value is created fundamentally rewrites the day-to-day workflow of software engineering. Let's compare AI engineering to traditional machine learning engineering. The sources point out that the entire pipeline has been violently reversed.
Violently reversed. I like that phrasing. In traditional ML engineering over the past decade, the workflow was strictly linear. Data, then model, then product.
Walk me through the friction of that old data model product pipeline.
Okay, imagine you wanted to build a feature that automatically categorizes incoming customer support tickets. Under the old paradigm, you couldn't build any product UI or get any user feedback for months.
You're just flying blind.
Totally blind. First, you had to extract a massive historical data set of tickets. You had to pay a team to manually label them into categories. That's the data phase.
Months of tedious work.
Then you hand that data to your data scientists. They spend months selecting an architecture, training a custom model from scratch, tuning hyperparameters, running validation tests. That's the model phase.
Still no user feedback.
Still nothing. Only after a massive capital and time investment, perhaps 6 to 9 months, did you finally have an artifact you could wrap in an API and prototype as a product.
And you put that product in front of users and they hate the interface, or they want completely different categorization tags.
You just burned millions of dollars in a year of engineering time. The iteration cycle is glacial.
AI engineering completely inverts this. Because incredibly powerful general-purpose foundation models are available on day one via API, the workflow is now product, then data, then model.
Product/data, not model. How does that change the sprint cycle?
A single full-stack engineer can prototype the entire feature in an afternoon.
An afternoon?
Yes. You mock up the UI, you write a zero-shot prompt outlining the categorization rules, and you send the live support tickets directly to a Frontier model API. You immediately deploy this MVP to internal users and measure if it actually solves the business problem.
Instant market validation.
Yeah, the API cost might be slightly high per transaction,
Yeah.
but you haven't spent a dime on custom model training.
So you only invest the heavy engineering resources into custom data pipelines or model fine-tuning after the product has proven its value.
Exactly. Once you need to optimize for latency, unit economics, or specific edge case accuracy, then you do the hard work.
This is a massive leverage multiplier for a back-end engineer. You can build complex, intelligent features at the speed of thought. But you just mentioned fine-tuning. The sources emphasize that AI engineering is much more about adaptation than training from scratch.
It is.
What is the actual technical trade-off between just sending complex prompts to an API versus fine-tuning a model?
It's a spectrum. a spectrum of cost, complexity, and behavioral permanence. Prompting or context construction happens at inference time. You are not changing a single weight inside the neural network. You are just utilizing its existing logic.
So it's fast and flexible.
Highly flexible. But you are constrained by the context window limit, and stuffing a massive prompt into every API call increases your latency and cost per token.
Whereas fine-tuning actually alters the model.
Yes. In fine-tuning, you take an existing open weights model, like Meta's Llama 3, and you resume the training process on a much smaller, highly curated dataset specific to your task.
Like formatting medical records into a strict JSON schema.
Right. But didn't we establish earlier that training models requires massive GPU clusters?
Training from scratch requires that. But fine-tuning utilizes techniques like LoRa low-rank adaptation.
How does LoRa work?
Instead of updating all 70 billion parameters, LoRa injects small, trainable rank decomposition matrices into the transformer layers. You freeze the massive pre-trained weights and only train these tiny new matrices.
Oh, wow.
Yeah, this reduces the memory requirements so drastically that you can often fine-tune a model on a single consumer-grade GPU in a few hours.
That is incredible. So the trade-off is prompting is for rapid iteration and general tasks, but once a feature is validated and hitting high volume, you collect the logs of those interactions, use them as training data, and fine-tune a smaller, cheaper model to handle that specific task perfectly.
Exactly. The fine-tuned model becomes highly specialized, significantly reducing your latency and operational costs compared to calling a massive frontier model API for every single request.
But whether you are prompting a massive model or fine-tuning a small one, there is a gaping hole in this entire development lifecycle.
And that is evaluation.
Yes. As a back-end developer, this is the part that keeps me up at night. Evaluation is widely considered the most intractable problem in AI engineering right now.
Think about traditional CI/CD pipelines. If I write a Python function that sorts an array of integers, writing an automated unit test is trivial.
It's just an assertion.
Right. I assert that the input 3, 1, 2 must return exactly 1, 2, 3. If it doesn't, the test fails, the build breaks, and I get an alert. The state is binary. It's objectively verifiable.
But how do you write a deterministic unit test for a probabilistic output?
You really can.
In traditional ML, it was still somewhat binary. A classification model either labeled the image a dog or it didn't. You could calculate precision and recall mathematically.
The foundation models produce open-ended generative outputs.
Exactly. If your application asks the model to draft a polite email to a client declining their proposal, there are infinite technically correct strings of text it could generate.
How do I write a Python assertion script that automatically checks if an email is polite? You can't. You can't use string matching. You can't use regular expressions.
Which means your continuous integration pipeline completely breaks down. You push a tweak to your system prompt, but you have no automated way to know if that tweak subtly degraded the model's ability to be polite across thousands of edge cases.
So how are engineering teams actually solving this in production?
The field is rapidly experimenting. One of the most prevalent, albeit somewhat paradoxical, methods is called LLM as a judge.
Using an AI to grade the AI.
Yes, you use a massive, highly capable frontier model like GPT-4 to evaluate the output of the cheaper, faster model that you're running in production.
So you build an evaluation pipeline.
Right. You feed the production model's output into GPT-4, along with a strict grading rubric. You prompt GPT-4 to act as an impartial judge and score the output on metrics like fluency, relevance, and factual consistency, outputting the score as a structured JSON object.
I mean, that feels like a house of cards. We are relying on the probabilistic reasoning of a black box model to verify the probabilistic reasoning of another black box model.
It is absolutely fraught with edge cases. Models have inherent biases. They often prefer longer answers, or they prefer answers that match their own internal writing style. You have to constantly calibrate the judge model.
It's not a silver bullet.
However, despite the philosophical flaws, empirical studies show that LLM as a judge correlates surprisingly highly with human expert evaluation, and it operates at a scale and speed that humans simply cannot match.
It's the best bad option we have for text generation. But the sources highlight another evaluation method that is far more robust, and it perfectly explains why one specific use case has exploded in popularity.
Functional correctness.
Yes, functional correctness. Explain that one.
You design the task such that the model's output can be objectively and deterministically verified by an external system. If you ask an LLM to generate a Python script to scrape a website, you don't need another LLM to judge if the script is good.
You just execute the script in a secure sandbox.
You run the compiler. If it throws a syntax error, the output failed. If it runs but returns an empty array instead of the scraped data, it failed the unit test.
The deterministic compiler becomes the ultimate, infallible evaluator for the probabilistic AI.
This creates a beautiful closed-loop feedback system. You can even pass the compiler error back to the LLM and ask it to debug its own code, iteratively looping until the test passes.
Which brings us to the final, most pragmatic section of this deep dive. We've mapped the stack, we understand the workflow inversion, and we know how hard it is to evaluate these systems.
Time to look at the real world.
Exactly. Let's look at the actual empirical data on where AI engineering is generating undeniable business value today. We have to start with the absolute juggernaut: coding and workflow automation.
Across every industry survey, software engineering is the most proven, economically viable use case for generative AI, and the data validates the hype.
There was that massive study by McKinsey, right?
Yes. They analyzed developer productivity using AI copilots, and the results are staggering.
We aren't talking about a 5% optimization here.
Not at all. For routine tasks like writing code documentation, AI reduces task completion time by 45 to 50%.
Half the time.
And for actual code generation translating business logic into functional code, it reduces completion time by 35 to 45%.
If you are an engineering manager and your entire team suddenly becomes 40% faster, the economic implications are profound. You are effectively expanding your engineering capacity by nearly half without increasing headcount.
And the tools are moving rapidly from stateless copilots, where you just highlight code and ask for an explanation, to stateful, autonomous agents.
The sources highlight tools like Agent GPT.
Yes, with agents, you don't just ask it for a script. You give it an objective, like extract the pricing tables from these 50 PDF vendor contracts and load them into a Postgres database.
And it just does it.
The agent autonomously breaks the objective into steps, writes the extraction code, executes it, handles the PDF parsing errors, formats the JSON, and inserts the rows.
There's also the explosion of text-to-SQL interfaces. Non-technical product managers can type a complex analytical question in plain English, and the AI translates it into a highly optimized multi-join SQL query, executes it, and renders a dashboard.
Or tools where a designer uploads a static screenshot of a UI, and the AI generates the functioning HTML, Tailwind CSS, and React components to replicate it perfectly.
If we look at the strategic macroeconomic impact of this, it threatens to massively disrupt the outsourcing industry.
Historically, tech companies outsourced the lower-level repetitive development work, building simple CRU interfaces, writing boilerplate integration tests to cheaper offshore agencies.
But if your senior in-house engineers can automate those exact tasks instantly with AI agents, the financial incentive to offshore diminishes. Teams will stay smaller, denser, and exponentially more productive.
That is a tectonic shift for the software labor market. What is the next major category of proven enterprise value?
Image and video production, particularly within marketing and creative workflows. We discussed how hard evaluation is for text because there is no single correct answer.
Right.
That exact probabilistic nature makes AI spectacular at creative tasks where you want a vast space of aesthetically pleasing possibilities.
Midjourney is the prime example here.
The scale of Midjourney's success is unprecedented. According to the data in the sources, by late 2023, after only operating for about 18 months, Midjourney was already generating roughly $200 million in annual recurring revenue.
$200 million. Wow.
They achieved this with a tiny engineering team and entirely bootstrapped, zero venture capital. It proves intense product-market fit.
But this isn't just about consumers generating fantasy art. The enterprise applications fundamentally alter unit economics.
Consider a global marketing campaign. A brand shoots a promotional image of a car. Traditionally, adapting that single image for different global markets required expensive editing or reshoots.
You'd need a whole team for localization.
With AI workflows, they ingest the base image and programmatically generate hundreds of localized variants. They can instantly swap the background from a sunny California highway to a snowy European mountain pass, adjust the lighting, change the demographic of the driver.
They can A/B test 100 different visual variations at near zero marginal cost.
The cost of asset generation approaches zero. Let's pivot to the use case that touches almost every knowledge worker: writing, information aggregation, and our RGAG architectures.
The MIT study cited in the book provides hard empirical data on this. They conducted a controlled experiment with college-educated professionals, assigning them occupation-specific writing tasks like drafting press releases, internal memos, and analytical reports.
Half the group was given access to ChatGPT. The control group was not. What were the actual metrics?
The group using the LLM experienced a 40% decrease in the time required to complete the tasks.
Huge time savings.
But the most critical finding is the quality metric. In traditional workflows, rushing to finish a task 40% faster usually results in a severe drop in quality. But independent evaluators scored the AI-assisted group's output quality as 18% higher than the control group.
A 40% reduction in time and an 18% increase in quality. That shatters the traditional speed versus quality trade-off.
And when you combine this generative capability with the RAG pipelines we discussed, you unlock massive enterprise value through internal knowledge aggregation.
The talk-to-your-docs paradigm?
Exactly. Large corporations possess massive repositories of unstructured data, decades of legal contracts, HR policies, technical architecture decision records.
Finding information in those systems is historically a nightmare of keyword searches.
But by layering a RAG pipeline over this data, you turn a static, dead repository into a conversational agent. A compliance officer can simply ask, what were the security audit findings for the European Payment Gateway in 2022?
And the system retrieves the exact PDF, extracts the relevant paragraphs, and synthesizes a direct answer.
It compresses hours of document review into a sub-second API response.
The final category the sources explore is education and conversational bots. And this sector perfectly illustrates the existential risk and the massive opportunity of AI engineering.
Education is the canary in the coal mine for AI disruption. The sources highlight the dramatic cautionary tale of Chegg.
Chegg built a massive, publicly traded business model around providing students with homework help and textbook solutions via a paid subscription.
And when ChatGPT launched, students immediately realized they could bypass the subscription and simply paste their homework questions into the LLM for free, instant, and often better explanations.
The market reaction was brutal. Chegg's stock price collapsed from $28 down to around $2.
Their core value proposition was instantly commoditized by a generalized foundation model.
But while Chegg collapsed, other organizations in the exact same sector thrived by leaning into the technology.
Organizations like Khan Academy and Duolingo aggressively adopted AI engineering. Instead of viewing the LLM as a threat, they utilized it to build features that were previously impossible.
Khan Academy engineered Kanmigo, right?
Yes, which uses complex prompt engineering to act not as an answer key, but as a Socratic tutor. It explicitly refuses to give the student the answer.
That's a clever use of system prompts.
Instead, it analyzes the student's mistakes and generates personalized guiding questions to help them arrive at the solution themselves.
And Duolingo dynamically generates highly personalized language practice scenarios based on the specific grammatical structures a user is struggling with. This highlights the core tension in Layer 3 application development, defensibility.
Chegg was vulnerable because their product was just retrieving static answers, something an LLM does natively.
Right, but Khan Academy is defensible because they engineered a complex, stateful workflow around the model.
If you are an engineer building an AI application, you have to assume that the foundation models will rapidly consume generic use cases. If you just build a thin UI wrapper that passes a user's text to an API and prints the response.
OpenAI or Anthropic will inevitably release that as a native, free feature in their next update. You have no moat.
So how do you survive? How do you build an application that won't be obsolete in 6 months?
True defensibility stems from deep workflow integration and proprietary data. Don't build a generic chatbot that answers questions about insurance.
Build an autonomous agent that deeply integrates into the specific painful reality of an insurance adjuster's workflow.
Build an application that authenticates with the legacy mainframe, reads the policy constraints, parses the unstructured data from an emailed claim PDF, cross-references it against a proprietary database of historical payouts that only your company owns, and automatically draft the approval transaction for a human to review.
The value isn't the AI generating text. The value is the software engineering surrounding the AI, handling the authentication, managing the API unreliability, parsing the messy real-world data, and executing the final state change in the database.
The messier and more entrenched the business logic is, the harder it is for a generalized model update to replace your application.
That is the essence of AI engineering. It is not about abandoning traditional software architecture. It is about extending it to orchestrate these new probabilistic engines.
Let's pull all of this together. If you are a back-end engineer listening to this, the barrier to entry into the AI space is an illusion. You do not need a PhD in machine learning.
You do not need to understand the calculus behind gradient descent.
Because of the model as a service paradigm, the heavy lifting of layer 2 is abstracted away. What you need are the exact skills you already possess.
You need to know how to architect scalable systems, how to manage API rate limits and timeouts, how to structure data pipelines, and how to build robust, fault-tolerant applications.
You just have to adapt to the new realities. You have to understand that tokens are the new compute bottleneck. You have to understand how to vectorize your data for RGAP pipelines.
You have to embrace the workflow inversion, mocking up products with prompts before you invest in data pipelines or model fine-tuning.
The modern AI stack is, at its core, just the new software stack. The foundational principles of building reliable, secure, and useful systems haven't changed. Only the primitive components have evolved.
It's just a new tool in the toolbox.
But I want to leave you with one final, highly speculative thought to ponder on your own. We just looked at the empirical data showing that the absolute most successful use case for AI right now is writing code. It makes software engineers 40% faster.
It's an incredible boost.
So if AI engineering is currently defined as humans writing code to connect users to AI models, and the models are getting exponentially better at writing code, how long until the AI models are the ones architecting the RAG pipelines, managing the vector databases, and writing the AI engineering code themselves?
It creates an accelerating recursive loop. The technology optimizes the very discipline required to build the technology.
Exactly. When the underlying code practically writes itself, the most valuable human skill in software development is no longer syntax memorization. It is the ability to deeply understand complex human problems, design the architectural systems required to solve them, and navigate the probabilistic chaos of the new stack.
The paradigm has shifted.
Don't wait on the sidelines. Dive into the API documentation, build a prototype this weekend, and stay ahead of the curve. Thanks for joining us on this deep dive.